In this first of three lectures, we're going to be looking at estuaries. In this short video, I'm just going to be talking about the classification system used for estuaries and how we can look at two simple, very simple metrics to determine the essential type. They're important for a lot of reasons. They're a nursery ground for a lot of animals like flounder and shad and crab. It forms a principal habitat for things like clams and birds. There's a large portion of the human population lives within about 100 kilometers of the coast. So there's a strong interaction between humans and the estuaries, and there's a lot of concern about loss of habitat and the effluents from wastewater systems reaching these habitats and modifying the ecological productivity of them. There's four types of estuaries when we look at from the point of view of their formation. So these are very long timescales. These are geologic timescales leading to the development of these estuaries, which can persist in some places for a very long time. In other places, estuaries and geological time come and go. The first is a drowned river valley. An example of that would be the Chesapeake. Essentially, during the last ice period, ice had consumed much of the waters of the world, was tied up in ice, so the sea level is about 100 meters lower than it is now. As these began to melt, they formed rivers, runoff rivers, very large scale, which essentially scoured riverbeds. You can still have a sense of the Chesapeake runoff in the canyons that lead from the Chesapeake off the shelf. They're underwater now, but at one point they were the riverbed of the Chesapeake. Eventually the sea levels rose again, back 100 meters up off the shelf to where we are today, drowning these old valleys. Fjord built, you can consider glacial built as the glaciers come out of the mountains. They push ahead of them a large amount of sediment, scouring in front of them like a bulldozer. And when they begin to recede, when they reach the edge of their extent and recede, and they don't actually move backwards, they're melting faster than they're moving forward. When that leading edge recedes, it leaves behind what's called a moraine, a terminal moraine, shown in the figure here. Example of a terminal moraine from the last glaciation, the Laurentide glaciation, are the islands of Nantucket and Martha's Vineyard. Once it leaves that behind, if we look at a profile of the resulting valley, you have these fjords, and the fjords are separated from the ocean by this moraine, and often the moraine can come within a few tens of meters from penetrating the surface, and what it does is it regulates the exchange of water between the fjord and the open ocean, not dissimilar from George's Bank being a prominent feature, but although that it is not a terminal moraine as we understand it. Third is a bar-built estuary. These are extremely common in our area. We have sand spit, so you have some source of fresh water, might be a small river or an area where you have a lot of groundwater. And so there's a source of fresh water trying to reach the bay, but along the coast, you have these longshore drift, and we talked about that in the Tuesday lecture when we went over sediment transport. So essentially, you have the freshwater trying to maintain the opening to this inlet or harbor, and the factors of sediment transport trying to close it. And sometimes one will win out of the other. You can have partial closures, and then they reopen again during a storm. But these are quite common. You see spits all over, in particular Cape Cod. And the last is a tectonic. A great example of that is San Francisco Bay, where you have plate movement leading to the formation of an estuary or a bay. This is a general schematic of an estuary. We'll return to this point over and over again. Key thing is that they're long, generally narrow compared to their length. And when I think of length, I'm thinking between where the freshwater forcing comes in at the river and the open boundary, which is where it's forced by tides. And those are two key ingredients of an estuary, to have the tidal forcing and the river flow. There are many places where groundwater is the primary source of the fresh water, and so those sources tend to be more diffuse along the edge of the estuary. But they tend to be long compared to their width, and they're small. Both these dimensions will be small enough that rotation does not play a strong role. The Earth's rotation does not play a strong role in the dynamics of the estuary. The key driving force is fresh water introduced by the river, so it sets up a pressure gradient which is going to force fresh water, which is lighter than the seawater, so it will float on top, it will stay near the surface, out towards the opening. But it doesn't move as a slab on top of the heavier water slab. There is mixing that occurs at the interface between these two fluids. And what the mixing will do is it will entrain the heavier, saltier, open ocean water into this layer, creating, increasing the salinity of that layer. And as the layer moves out, as this fresh water moves out, it's getting saltier and saltier as it entrains the high salinity or higher salinity open ocean water. It's entraining that volume of water as well, and that has to be replenished, and that's replenished out here at the open boundary. So in the net, you have this two-way flow. Now, during the course of a tidal cycle, the entire flow could be in or out, but when you average over a tidal cycle, you find out you have this two-way flow. You have inflow of higher salinity, open ocean or open bay salinity water, replacing the water that's been entrained into the upper level water, which is being driven by a pressure gradient, by the river, back out into the bay. So the two-way exchange is key because that represents a replenishment or refreshing of the water in the estuary. So the water in the estuary is not stagnant at depth. It can be quite active, and it can be overturning rapidly such that pollutants that are introduced in the estuary can be rapidly flushed out. Being able to quantify that turnover time means understanding the dynamics of the estuary and being able to get at some of the key numbers that we need to make a good estimate. So with tides, as I mentioned, the flow can be unidirectional, generally be unidirectional. So during flood, at a given station, if I put a mooring here with some ADCPs, I'll find everything's moving up estuary, towards the mouth of the estuary, towards the river, where it's generally shallower. On ebb, everything's moving down estuary. It's when I average over these two, I find out that I have this two-way balance, that at the surface, the ebb is stronger than the flood, and at depth the flood is stronger than the ebb, leading to a net flow, which I'll make this pink color, of out at the surface and in at the bottom when we actually average over a tidal cycle. And that's the key thing. What happens in the net over a tidal cycle? And this shows you a schematic of the salinity contours. You can see you have, even along the surface, it starts fresh and it slowly increases in salinity as we move downstream, and that's because it's entraining as it goes. It's entraining higher salinity water. You also see during a tidal cycle that these isohalides tend to get more vertical and then relax back as the water moves back and forth. So you tend to increase stratification on ebb and decrease stratification on flood. A key metric is the tidal prism, and this will come up in some of the discussion we have in later lectures as well. The tidal prism is simply the difference in the volume of water in an estuary between high tide and low tide. So high tide, there's more water. We subtract the water that we have at low tide, and the difference between that is this tidal prism. So if you have larger tidal range, you will naturally have a larger tidal prism. It's a pretty easy metric to get at because if you have some sense of the surface area of your embayment and you have some sense of the tidal range, you're just essentially multiplying those two together to get a volume. So it's, even with some simple maps and some simple knowledge, you can get a decent estimate of the tidal prism that will be handy because that will be used in some of the estimates that we come up with for time scales. Now we can classify estuaries. A key thing that that we need to consider is this balance. How much mixing is occurring, and how much mixing is occurring can be related back to two very simple things. The first is the river discharge. R is a volume. It's this volume of fresh water discharged by the river over a tidal cycle. So that's related to how strong tidal cycles a fixed amount of time. So how big this volume is depends on the river, the freshwater river flux. Is it a big river? Is it a small river? Essentially, the river discharge. And the other is this tidal prism we just talked about. R is a proxy for how much fresh water we are putting into the system. V is a proxy for how much mixing the tides are able to do. The more tides are an energy source, and that energy source can go into mixing. And if you have greater mixing, then you have greater entrainment of the bottom water that will then need to be replenished. And then you will have greater turnover and therefore a smaller time scale of flushing to the estuary. So these two things are basically fighting each other. Greater volume of freshwater discharge means that you have a lot more fresh water, and that fresh water is going to inhibit mixing because due to maintaining the stratification, whereas the tidal prism will accentuate the mixing. So we're going to look at classify some estuaries simply based on the ratio of these two quantities, both of which are fairly easy to estimate. But keep in mind when we classify these that both of these can change with time, particularly the fresh water. It can have a distinct seasonal cycle. In our region, our monthly rainfalls are actually fairly similar. In some places like the Pacific Northwest, you can have runoff of snow in the spring. So May, June, you get a big pulse, and you also have a big pulse in the fall related to climate activity, storm activity. Other places like the rivers in Maine will have a very strong pulse due to snow melt as well in April, May, June timeframes. So R can vary over the year as well as V. V is a tidal signal. So we know even over the course of 14-day cycle, you can have a large range in the tides due to the spring neap variation. We're going to classify based on three ranges for this R over V parameter. Again, R is a river discharge, V is a tidal. It's the volume of river water introduced over a tidal cycle, and V is the tidal prism. First is a salt wedge. A salt wedge estuary has strong river forcing compared to the tidal prism, so R over V is greater than 1. This shows an upper view, a plan view of the estuary. Here's the river, station 1, station 2, and station 3 is closest to the ocean. Stop using this hideous color. And if we look at the profiles of salinity, we see closest to the river, we have strong mixing. So right up near the river, the mixing is strong enough, the tides are weak enough that essentially you have fresh water from top to bottom. At this at station 2, which is the mid-estuary station, you have a sharp halocline here. You have fresh water overlying saltier water, and as it goes downstream, some weak mixing will mean that we have this halocline will move up, and we will have, we can visualize this in a few slides as a wedge. Essentially, the pressure gradient of the river forcing is balancing this wedge of separating the high salinity and low salinity waters, but they may remain quite separate. So you have a sharp halocline, which means strong stratification, which means an inhibition of the mixing. The tides are not strong enough to mix down this halocline, and therefore the entrainment of the deep water is rather weak, meaning that the return flow is also rather weak because there's nothing to replenish. When we look at the net velocity profile, it looks something like this. So this is averaged over a tidal cycle. The ebb direction is to the right and the flood direction is to the left. So at the surface you have outflow, and somewhere in mid-depth is a crossover point, and below that you have some inflow, but it's rather weak inflow. Again, if we integrate this velocity profile, we'll have a net velocity profile because the net in the net, the estuary has an outflow. It must equal the river discharge. Otherwise, it will be filling up with time. So we're assuming the estuary is not filling up with time. So we have weak inflow associated with the weak mixing, associated with the strong river discharge, leading to large stratification. The second estuary, we've weakened the river discharge relative to the tidal prism. So now we have stronger mixing. That stronger mixing is going to weaken the halocline. You can see you have weaker haloclines here, meaning there's more entrainment, and more entrainment means more deep water that needs to come in to replenish that deep water that's been entrained into the surface layer. You can see that the return flow, the up estuary flow at depth, is stronger than it is in the salt wedge case. The net is still the same, so you have an enhanced outflow as well. Stronger outflow, stronger inflow. The last one example is where you have very weak river discharge compared to the volume, the tidal prism. This is probably closer to most of the estuaries in our region, where the tidal forcing is strong compared to the river discharge. In this case, the estuary is quite well mixed. You see very little stratification from top to bottom. You do not see any two-way flow because we're not entraining a deeper layer. There is no deeper layer. It's simply mixed from top to bottom. All you have is a gradient in salinity from 0 at the head to open ocean S0 at the end. And you can see that if you do profiles, they're all vertical. But as you move downstream from profile 1 to 2 to 3, you only see a minor variation and you only see minor stratification. So in this case, there is no two-way flow, and you simply have during flood, all the water moves in, ebb, all the water moves out, and on average, it moves out a bit more than moves in to make up for the river discharge that's being put into the system.